So I'm going to talk a little bit, maybe off topic in one sense, that I'm going to be talking about emitters and IR gas sensing. But let's get into it. I'm the Chief Scientific Officer of a company called 4K MEMS SA, and we are a family startup based in Switzerland. And we've developed the smallest, hottest, fastest MEMS thermal emitters in the world. When I mean small, this is, the laser is so bright that you can't see it, okay. When I mean small, this is the size of an emitter in comparison to Europe. It's 1.4 millimeters by 1.4 millimeters. When I mean hot, it's at 2000 Kelvin, which means that its spectrum is running right the way from part of the visible out into the mid-infrared. And it's fast because we can modulate it for a thermal emitter at more than 100 Hertz. And what we're doing with this, we're targeting embedded spectroscopy and consumer automotive gas sensing markets. So the key challenges that we had to overcome to make this device was to how to operate the device at 2100 Kelvin without buckling, and how to make a uniform temperature across the whole emitting area, and how to make it using a standard MEMS process. And the device you can see in the top right is basically a suspended membrane on springs. And when the device heats up, instead of buckling, it rotates. And what this means that the device stays in the same plane very well. The second thing is the springs are the heaters. So the heaters are outside the plate. So the plate has a uniform temperature to about 5 degrees. And then we wanted to make it using wafer scale packaging so that they can be made cheaply at high volumes. And we call it a star on a chip. So this is the device here. You can see it's in comparison to our pen. You have a single emitter here glowing very nicely. And we can take it directly from the dicing tape to the PCB with no other packaging involved. These are examples where we took the device, we put on solder paste to a PCB. So this is really ready for production. So the high temperature allows us to measure all wavelengths from the near to the sphere, which means we can look at identifying and measure organic materials, look at fitness, diet and health. We can measure like lactation in your skin, look at coffee analysis. The mid-range infrared is also good for gas and environmental modeling, and that's what I'm going to talk about here. So non-dispersive optical gas sensing is a system where we use an emitter which sends light out through our gas cell with 2 filters on a detector, 1 filter for the reference and 1 for the gas signal. And we basically compare the 2 one together and do some data analysis. On the top I've showed a system coming from Sensirium, which is typical for this. So we decided that we have a very small emitter, so it'll be very interesting to see what we can do to make a small gas sensing system. And this is where micro-optics comes into play. So first of all, our novel geometry. Because we can make small emitters on a wafer scale, we can also make filters on a wafer scale. So instead of having 2 detectors, we have 2 emitters, each one with its filter onto it. Then we put the 2 signals onto our detector and multiplex them. We need to check that our emitters are behaving the same way. And we do this by having a reference silicon photodetector. And so what you see we've done is we've removed one of the IR detectors and replaced it with a silicon detector. And the advantage of this is numerous. And due to the shape of the blackbody spectrum, its sensitivity to emitter temperature is much higher here than at these wavelengths. So we have a very sensitive way of checking what the temperature is. The second one, of course, the silicon detectors are really cheap in comparison to IR detectors. And finally, the noise level of silicon detectors is very small. So we can use them to detect basically stray light which we're not using in the system otherwise. So how to implement this? Well, this is the role of the Fabulous project. We want to make a single module with our emitters, our silicon fusion detector, and the filters. And you see it on the right here. It's a device where we have microlenses which were fabricated by Focuslight, filters which were fabricated by Viavi, and then the whole system was put together by CSCM. And with this kind of system, we're beaming the light with the microlenses. We can collect the light with the compound parabolic concentrator onto our detector. So this is the microlens design. It's supposed to have a radius of curvature of 1.4 millimeters. Its divergence is about 8 microns due to the size of the emitter, which is very nice for our system. The lenses which were fabricated by Focuslight, they were profiled and the measurement was basically perfect. 1.4 millimeter radius of curvature plus or minus 30 microns. Excellent job by them. The devices were then mounted by CCM at Almanac, and the beam profile was measured in Neuchâtel. On the left you can see the experiment at 2 different distances, one close, one further away. In the middle is the simulation from ZMAX, which looks very nice. And the right is where we take into account the size of the detector, which is 2.2 millimeter in the simulation. As you see, the left and the right panel agree very, very nicely. We even see an extra feature, which was initially a surprise. We see a side lobe here, and this is because we have 4 lenses. And one of the emitters, some of this light is going at a high angle through the second lens, and we're collecting it here, and we see it both in the experiment and in the simulation. So the conclusion is the microlenses are performing as designed, and they are well aligned with the emitters. We wanted to test this in a gas sensing setup, so we used a Broadcom evaluation kit. This is a system which you see in the middle, where we have this original emitter, which you see is very large in comparison to our small emitters, and we have paraelectric detectors. And the question is, we've gone from this very big emitter to our very, very small emitter. It said, can we maintain the same performance? And it says, we can because of our microlenses, and because our devices are much hotter. So, how we calibrate the system, we call it the leaking box principle. We basically put our experiment into a box with CO2 in it, which leaks out very slowly. We have 2 other CO2 detectors into it, and you look at this decay, which you see on the right is basically exponential. We fit this decay, and then we can basically calibrate the system. When we use this, as I said, this is the original Broadcom system. This is our decay, and on the right we show, sorry, on the left we show the comparison, the deviation of the fit, and you see it's roughly around 20 ppm, which is shows that the 2 systems are working very nicely. Then we took out the Broadcom emitter, we put in our system with microlens arrays but no filter. We did the same experiment, and again we see this very nice comparison between the Sensorion device and the 4K MEMS device, and again our deviation is of the order of 20 ppm. So finally, we put all this together. We got our system with our emitters, our microlenses, our CPC, we put them together in the top layout. The analysis was slightly more complex because we have to do this multiplexing, so we have to turn our 2 emitters on and extract the signal. And then once again, this is the decay. You see here the time scale is very long, it's decaying very slowly, which gives us lots of time to have lots of measurements. And then we can look at the absolute deviation of the system from the baseline. And you can see the standard deviation, in this case, is around 10 ppm. So what this shows is that we can take our small block and we can measure CO2 as you would in a standard system. And this is thanks to the work in the Fabulous project. So to conclude, I've shown that we have a novel MEMS thermal emitter for 1 to 5 microns. The device can be made wafer scale, and very small devices allow miniaturization. We've shown that we get significant power for CO2 sensing despite the small size, and this novel NDIR scheme has been demonstrated by taking advantage of the wafer scale manufacturing of microlenses and filters. With that, I would like to thank you and acknowledge the people from all the companies who are involved in this fabulous project.